we will find general solution to this system of equation in the matrix form. In the matrix form, we will find the eigenvalues and then eigenvectors and write the solution from there. First, the eigenvalues. To find the eigenvalues, we will solve the characteristic equation. Determinant of A minus lambda I equal to 0. That is the characteristic equation. So we have determinant of, I will just copy the matrix A. And then we minus lambda on the diagonal. Because the I matrix is just 1 on the diagonal. And when we multiply lambda, we have lambda on the diagonal, and then we subtract. So that's what we have. Right. Determinant of this matrix must be equal to 0. Right. For 3 by 3 determinant, we can evaluate along any row or any column. I choose the first row, so we'll base off the cofactors with the element on the first row. So first entry, we have minus 1 minus lambda. Now, first, if we cover the row and the column containing that entry, what we got left is this 2 by 2 matrix, and we just evaluate the determinant of that 2 by 2 matrix. So we'll have 2 minus lambda, 1, and 9 minus 1 minus lambda. So that's the first entry. Now we go to the second entry. We will cover the row and the column, and we have left with a 2 by 2. So we're going to have 1, 1, 1, 0, minus 1, minus lambda. Now, make sure that we have the sign chart as well. So the sign chart for a matrix, we always start with the plus, and after that the sign alternating like chessboard, like that. So the 1 standing on the negative sign, so that should be negative. And then we have a 0 cover the row and the column containing 0. We're left with this. It doesn't matter what it is, because 0 times anything will be 0 anyway. But I'm just going ahead and write that out. And the 0 will stand on the plus sign. Remember, plus minus plus. So that will be 0. Right. Now we just multiply them out and evaluate. And so for this polynomial equation, right, 2 minus lambda minus 1 minus lambda. Again, 2 by 2 determinant. We multiply this direction, this diagonal, subtract the other diagonal. Minus 9, and then minus 1, minus 1 minus lambda, and minus 0. So that's pretty much it. 0 times anything, that goes to 0. So that's what we have. And multiply it out. minus 1 minus lambda. 2 times minus 1 is minus 2 with the minus 9 here, make it minus 11. 2 times negative lambda, so minus 2 lambda plus a lambda, so minus lambda plus lambda square minus minus the negative 1 is the plus 1 minus a negative lambda is the plus lambda equal to 0, and multiply this. Sorry, I forgot the parentheses about here. Multiply it out. Negative 1 times 11, negative 11, sorry, positive 11 lambda minus lambda square plus 11 lambda plus lambda square minus lambda cube plus 1 plus lambda equal to 0. Combine like terms, we have negative lambda cube and then the lambda square cancel out. And then 1 lambda, 12 lambda, 13 lambda. And 11 and 1, so that will be 12. Right. That is a qubit equation. We should use a calculator on this one because there's a qubit formula, but that's a bit complicated. I just enter the function in here, x instead of lambda, so negative x cubed. I just use that, 13x plus 12, and then hit graph. Look like there are 3 solutions. So we have lambda equal to negative 3, lambda equal to negative 1, and lambda equal to 4. So those are the eigenvalues. Of course, if we're not sure about that, or if we want to check our answer, we just say lambda minus negative 3, lambda minus negative 1, and lambda minus 4, and we just multiply this out. Of course, we can also throw in the negative. It doesn't affect anything. But if you multiply it out, we should get back to the polynomial we had earlier. Right. So anyway, we have 3 eigenvalues like that. Let's call this one 1, 2, and 3. So we found all 3 eigenvalues. Next, we find eigenvectors. To solve the eigenvectors, we will solve this equation. Instead of determinant of A minus lambda I equal to 0, that is the characteristic equation. We will solve this equation, A minus lambda I. This is in the matrix form, so we have a 0 vector instead of a 0 number. Right. Remember, we have 3 eigenvalues, so we have to do for all 3 of them. First, for eigenvalues of negative 3, we have A minus lambda I. I'm going to write the matrix A, original matrix, negative 1, 1, 0, 1, 2, 1, 0, 9, negative 1. And then minus lambda on the diagonal, so will be plus 3, minus negative 3 is plus 3. So I add 3 on the diagonal. And multiply by the column. Right. So in that case, the diagonal will become 2, 1, 0, 1, 5, 1, 0, 9, and 2. V1, V2, V3. Right. We will use the calculator to solve this system of equation. I'm going to use reduced row echelon form from that. Let's just put that here. Right. Second matrix, go to math and go down to reduced row echelon form. Will be this option here. And we're going to put a 3 by 4 matrix. Uh, 2, 1. The last column will be the 0, 0, 0 on the right hand side. So we have 2, 1, 0, 1, 5, 1, and 0, and 0, 9, 2. And we hit that. If we convert this to fraction, that is what we have. I'm going to copy the result. 1, 0, negative 1 over 9, 0, 1, 2 over 9, 0, 0, 0, and then we have 0, 0 on the right hand side. Right. And give some space here. Alright, next what we see is from the first line. Now we look at this first line. We should have V1 minus 1, 9, V3 equal to 0. So V1 minus 1 over 9, V3 equal to 0. The second line, V2 minus 1 over 9, V3 equal to 0. The third line gives us nothing. Now, in linear algebra, whenever we have the 1, that is called the pivot entry, and we have the 1 here. Corresponding to this, we have V1, V2, and V3. Of course, that's where we get the coefficient from. However, when we look at that, we see there is the missing pivot entry in this V3 column. So there's no pivot entry in V3. Because of that, we see V3 is arbitrary, or we just say V3 is free. It's free to choose. We can choose that to be anything, or arbitrary. Right. Now if we write those like that, from this equation we can say V1 is equal 1 over 9 V3, and V2, sorry, I copied it wrong. That should be plus 2 over 9. Sorry, should be negative 2 over 9 V3, and V3 is just free, so you can just say V3 is just itself. Right. Or if we put in the matrix form, we have 1 over 9 V3, negative 2 over 9 V3, and V3 here. I write a little more step than it should. So we factor out V3, we have 1, 9, negative 2 over 9, and 1. if we want to, we can choose this to be the eigenvectors. But eigenvector is the whole space, so we can choose something that is nice and even. So what I usually do is, why don't we just multiply everything by 9? And so we have the vector of 1, -2, and 9. And that is, let's see, call that V1, the eigenvector 1. Corresponding to that eigenvector, we have the eigenvalues of 3. Right. We do the same thing for eigenvalues of -1 and 4. I did that beforehand, so we don't have to spend less time on the problem. Right. So the same thing, we solve this equation, A minus lambda I V equal to 0 vector, and we solve that, reduce to echelon form. And again, we have 1 on this column, 1 on this column. There's no pivot entry on that column. So in which case, we say V3 is free. And then the first row give us 1v1 plus 1v3 equal to 0. The second line, v2 is equal to 0. And then we write the solution and factor out v3. And we have the vectors -1, 0, and 1. That will be the eigenvalues, eigenvector number 2, corresponding to this eigenvalues of 2. And the same thing for eigenvalues of 4. We have the eigenvector of 1, 5, and 9. And then we just write the solution. The solution will be in this form, the vector form C1 E lambda 1 T times eigenvector V1, C2 E lambda 2 T eigenvector V2, and C3 E lambda 3 T V3. Where we put everything we have for this problem, we will have C1 e to the -3t, and the eigenvector V1, 1, -2, and 9, and C2 e -1t, which is -t. Eigenvector will be -1, 0, and 1. And then C3 E 4t, the eigenvector 1, 5, and 9. So let me try to put the whole problem in one page. Cannot really do that. Yeah. Yes, that's what the whole problem is on the screen now. So we just find the eigenvalues, the eigenvectors, and then put the linear combination. The solution will be in this form. And that's what we have.